Let's go over the ripple tank video I made at school. Here's a side view of the light shining down through the water, through the glass, and then down onto the table. When the light rays strike a crest, the crest acts like a lens, focusing the light and concentrating it on the paper. The crest appears as a bright region on the paper. The next crest does the same thing. So what's in between the two bright regions? There's a lack of light at the trough. This occurs due to a change in speed of the light as it enters the water. It's called refraction, and we're going to study this more later. What we didn't see in my video was the pattern formed on the ceiling. Some of the light that comes down to the water reflects off. A crest causes this light to spread out. Now, can you see where the concentrated light appears? It's going to appear bright above a trough and spread out so darker above the crest. You should be able to see this in your house when you shine a flashlight onto the tray of water. So it's the exact opposite of what we saw shining through onto the paper. So what did we see when I put my finger in the water? We saw the waves spreading out in a circle in all directions. This is called a point source. But I also had a ruler that I could put in the water and give it a quick shove. The waves were flat wave fronts moving forward with some curvature on the ends. We want to ignore that curvature and focus on the part that's going straight. Now this is a flat or a plane source. If I dip my finger in the water slowly up and down, I get waves moving outward. And what would it look like if I moved my finger up and down quickly? High frequency. I have a shorter wavelength. I have more waves in the same space. The frequency does not affect the speed. It's the same speed. It's the medium that affects the speed, and that would have to do with things like the depth of the water, perhaps. But it's the same depth of water, same speed. You can see it with this relationship. Now we talk about reflection. I put my barrier in the water, and I took the ruler and I shoved it toward the barrier. Ideally, the waves should be completely flat, going toward the barrier. The red arrow represents what's called a ray. It shows the direction that these waves are traveling in. After the waves bounce off the barrier, we see them moving outward like this. We can trace the ray. We draw a line normal to the surface of the barrier. It's called the normal line because it's perpendicular to the surface. We can measure the angle of the ray that's coming in to strike the barrier from the normal line. It's called the incident angle. Then we can measure the angle of the ray leaving the barrier, measured from the normal. It's called the reflected angle. If you do the experiment at home or you study the video, you find out the angle of incidence equals the angle of reflection. This is the law of reflection, and it works whether that barrier is straight or if it's curved. Then we put a concave reflector in the water and made a wave approach. And they're pretty flat as they come into the reflector. But when they bounce off, they seem to get concentrated. They actually go through a point. That's called the focus. And then they pass through that focus and keep on going. So how does that work? We draw an array. We draw in a normal line. It has to be perpendicular to the surface where the ray strikes that surface. That's the angle of incidence, and the angle of incidence has to be equal to the angle of reflection. So the ray bounces off like this. Well, we can do the same at any ray. These rays intersect. That point's called the focus. All of the waves reflect and go through the focus. We say that a concave reflector is converging. Then we use the convex reflector. The plane wave approaches the reflector and bounced off, curving such that it's spread out. We can explain this by drawing the rays. We draw a ray, we put in a normal line, and measure the angle of reflection to be equal to the angle of incidence. We can do the same thing with another ray. In fact, all of the rays will do the same thing. The normal line is going to be different for each one of these depending on where it is on the surface, because the surface is curved. So we can see that the reflected waves spread out. And we say that the convex reflector is diverging. Then we set up two barriers with a space between them and made a flat wave approach the barrier. We're interested in the part of the wave that passes through the opening. Much of the wave in the middle passes through and keeps going straight, but the end of the wave is now acting more like a point source spreading out. This phenomenon is known as diffraction, the spreading out of a wave as it passes through an opening in a barrier. Then we made the opening smaller. We got a much more uniform curvature. There was nothing left that was straight. It was all curved. Diffraction increases when the opening gets smaller. With a small opening, there's really nothing flat left. It's just a point source. And then I lowered one end of the wave tank and made a deep area, had a shallower area, and then the beach up here. I made a wave with the ruler and it approached the beach. As it approached the beach, one end got into the shallow water while the other end was in deeper water. When the waves go into the shallow water, they slow down. That's because the waves start to encounter friction with the bottom of the tank. The deep side is still going fast. So the wave starts to curve. The wave advances a smaller distance than the part in the deep water because it's going faster out here, slower here. We say that the waves bend toward the beach. This is called refraction, the changing of the direction of a wave due to a change in speed. In the next part, we could measure the velocity of a wave because we put a meter stick down by the shadows and I marked off 30 centimeters to 60 centimeters. You can just count the frames, 30 frames per second, go that distance. I got 21 frames, 30 frames per second, 0.7 seconds, and I got 42.9 centimeters per second. Now in the next part, we used a point source and a mechanical oscillator to create a series of waves. The waves spread out and we could count the number of frames it would take for one crest to travel the 30 centimeters. I counted 24 frames with a time of 0.8 seconds. Now that's a little bit longer. Now in theory, we would like to see that that would have been the same as 0.7 seconds. But one, this is a point source, and the amplitude wasn't quite the same as the flat wave that moved. And in water waves, it's tricky. It's shallow water, so that could change the velocity a little bit. And so we get 37.5 centimeters per second. We could read the frequency on the machine as 12 hertz. We can now calculate the wavelength. That gives us 3.1 centimeters. How can we check this? Pause the video and then count the number of waves over 30 centimeters. I have a distance of 30 centimeters. I counted 10 waves. I get a wavelength of 3 centimeters. Not bad, pretty close. Did you notice what happened when we put the machine to 30 frames per second? It looked like all the waves were standing still. How come? The video is also shot at 30 frames per second. It's a stroboscopic effect. At school, I have a weight on a string and I can swing it around while I shine a strobe light on it. If the weight makes one complete circle and the light goes off, and then makes another complete circle and the light goes off, and then another complete circle and the light goes off, it looks like it's standing still. If the weight goes over to here and the light goes off, and then the weight goes over to here and the light goes off, and then it comes around to here and the light goes off, it looks like it's going backwards. In the last part of the video, we put in another source and made two sources overlap, and we created an interference pattern. We'll explore that in the next video.